For Katherine or Katie? But yeah, I heard you identify yourself as Katie. Yeah, I have no preference between David and Dave. Not at all, but somehow on papers it's respond equally. I have no preference. Most everyone just responds. I know. Just pick one. Tell me which one. Yeah. You'd be in the vast majority.
I was spending the last 20 minutes or so trying to think of a pun, and I don't know if it came to me, so let's see if something comes naturally, but I make no promises.
Okay. Yeah, I realized at some point there I was like trapped in like, you gotta just stick with it.
You gotta keep going, I know. All right, well, I'll rely on you then for this one.
If you supply it for me, that would be great.
Okay.
Oh, supply. We can talk about.
Oh, you got all after. Oh no, you're not doing the afternoon.
Supply. No, I'm trying to get a pun with supply limited.
Sure, yeah. I was gonna say like the replenishment talks, right?
Yeah.
But yeah. I don't think you're sharing those.
No, I'll come up with one for you.
All right, sounds great.
Okay. Welcome back to the second half of this exciting session where we've had talks so far about the solar system and exoplanets, ions and neutrals, escape and source of atmosphere. And so we're going to keep that train rolling along. I also want to tell you that during this part of the session, I'll either be switching from puns to limericks, or I will subvert the entire bingo card by just reading all of them off. So it's really up to you. Just feel free to shoot me a little message and I'll do one of those things. Or I'll stick with puns. Yeah, you'll find out. So the first presentation for this part of the session is from Katherine Bennett. Title is The Power of Coupling Transmission and Emission in Observing Atmospheres, the case of GJ 1132b.
Thanks, Dave. Thank you all. I will certainly not be providing a limerick for you, so please look to Dave for that. I'm gonna stand here, I think. Try that. How's everyone doing? Everyone caffeinated? Great. I'm a fourth year PhD student here at Hopkins, and I'm very excited to share this work with you all in coupling both transmission and emission spectroscopy or photometry together. I think that this is going to be a good avenue in the future for targets that you can do both of these to really provide much tighter constraints on atmospheres than we've been able to do so far with either method, assuming that we continue to look at a lot of non-detections in either case. So thank you, of course, to the organizing committee for establishing this conference and allowing me the chance to speak, and of course to all my collaborators on this work. This is out of the No Air collaboration led by Kevin Stevenson and Jake Lustig-Jaeger at APL. So thank you to them and everyone on this slide. So, you know, of course, this is the question that keeps us all up at night, I know. You know, which rocky planets actually have atmospheres, if any? And I think a lot of the community tends to try to answer this question like either using transits when we're actually measuring the wavelength dependency of the transit depth as the planet passes in front of its star, or by looking at the eclipse and trying to measure the day-side temperature of the planet when it passes behind its star. And of course, this lattermost technique, Hannah Diamond-Lowe gave a great overview yesterday, and that is the technique that's going to be used for the upcoming DDT program. And there are certainly reasons to favor one over the other in different cases, right? The main takeaway from my talk is that they're sensitive to different regimes of atmospheres, right? So if you consider a bunch of different types of atmospheres, we've already seen this kind of plot a couple of times this morning. If you have atmospheres of varying surface pressures, so you have low surface pressures up on the top of the y-axis and higher surface pressures at the bottom, and then as a function of different atmospheric weights. So I have the case of, I'm going to totally move because I feel like I'm looking behind myself, as a function of what the main constituent molecule is. So you have, perhaps water or nitrogen in an Earth-like case, or carbon dioxide. So these are getting heavier and more compact as you go over towards the right-hand side. So if we plop our solar system bodies on here, this is roughly where they would fall. And critically, a couple of things here. So transits are going to be less and less sensitive, or it's going to be harder and harder as you go higher and higher in mean molecular weight, because the mean molecular weight is going to shrink the scale height of the atmosphere, making the features themselves smaller to see in transmission. So that means it's going to be easier to detect, to go for eclipses as you move towards the right-hand side. Likewise, it's going to be easier to move towards eclipses as you get to higher and higher pressures, because a higher pressure means you're going to be able to redistribute that heat more efficiently, so your day-side temperature is going to be lower, making it easier to detect an atmosphere in an eclipse. Whereas on the other side of that, if you have a lower pressure atmosphere, it might be harder to actually detect that in eclipse. The heat redistribution might not be as efficient, so it's hard to tell if there's a thin atmosphere or if it is a bare rock. And this is where transmission spectra actually can play a stronger role, particularly at the lower mean molecular weight end. And I really want to emphasize, and I should say too, this isn't the only reason to pick one over the other. There are more logistics reasons, of course. Hannah talked a lot about the eccentricity concerns of eclipses. You don't have that with transits. If you just measure the period, then you can just extrapolate into the future. But on the other side, the pros for eclipses include the fact that they are generally better for hotter targets. A lot of our rocky planets are hotter. And the big issue is that the eclipse measurements largely avoid the issue of stellar contamination that I know many of us are very familiar with in our transmission spectra. But in either case, there is always going to be ambiguity when you use one method over another. You could have the flattest transmission spectrum, which I'm actually going to show you guys in a second. But you could still say, okay, well, there could still be just like a really thick haze layer, and we don't know, if it's bare rock or hazes. So similarly, you could have a thinner atmosphere that you could have an eclipse with a thinner atmosphere and not really know if it's a thin atmosphere or a bare rock. So if you can, use them both, which is what we did for GJ1132b, which is one of our near and dear rocky M-dwarf planets. It's a little bit larger than Earth, but it orbits on a 1.6-day orbital period, so it's pretty warm. The NOAIR team, we published a study using 4 transits with JWST NearSpec that just came out last month. And the spectrum is super, super flat if you combine all of the visits together. I'm happy to talk more about this too, but what I really want to emphasize is then we took the results from Chao Shui's paper that came out, that was last year already, right? A year ago, on the emission spectra of this planet, and their results showed that it's consistent either with a bare rock or some thin atmosphere scenarios, depending on the composition and surface pressure. And we attempted for the first time to try to put these together. So I'm going to show you kind of the real data version of the cartoon plot that I was just showing you. We have, again, surface pressure on the y-axis, mean molecular weight on the x-axis. I'm going to show you, it's a 2D contour plot of what what regions of parameter space our data are consistent with, and then we overplot the upper limits from the emission data. So we're just going to consider 3 cases here, even though this is a 2D plot. We're going to consider that carbon dioxide case first of a pure carbon dioxide atmosphere. And so you can see these gray contours are our limits. The darker the gray, the more it agrees with our data. So you can see that in the case of just transmission, we might think a carbon dioxide, 1 bar carbon dioxide atmosphere is consistent. However, you can see here, this is the upper limit from emission, and this upper limit is at a much lower pressure. So emission is actually provides a more stringent constraint than we can with transmission in the case of the CO2 atmosphere. You can do the same thing as we go down in pressure. I'm going to show you next the Earth-like scenario, assuming about 28, 29 AMU. In our case, you can see this gray contour kind of just like goes up all possible pressure regimes. So we're not really able to constrain which pressure regimes are ruled out in the case of an N2 atmosphere, versus again, the emission spectra does provide a more stringent constraint saying that it has to be less than a bar, right? Now the scenario flips when we go down even more, and when we look at in the case of a steam atmosphere, now transmission becomes more constraining. You can see that if you just consider this column again, our region that agrees most with the data is up here more in the millibar range, versus the emission data, can be down closer to 0.1 bars. So if you combine all of these, basically, this tells you, here is our Earth atmosphere at 1 bar. If you say like, okay, it has to be, much, much thinner in any case across any mean molecular weight. But if we remember that this is a 5 gig-year-old planet on a 1.6-day orbital period, we don't necessarily think that thin atmospheres are very stable, as Leonardo talked about earlier in his talk. So at this point, we can say that the simplest explanation given the data is a bare rock. And if we're being very conservative, we can still say that there are thin atmospheres that are consistent with the data, but they are much thinner across the board than we'd be able to say with either transmission or emission. So I was really happy to kind of tease into that. And of course, the big question is, can we do this across the board with all of our planets? So here are all of the rocky planets we know, and the colored points are observations that have been either executed or planned with JWST. I'm just plotting this as a function of the emission spectroscopy metric and transmission spectroscopy metric. So the best targets are going to be up here in the upper right-hand side. And in blue are all the planets that have been observed or will be observed both in transit and eclipse. And so I didn't know what I would see, but there are a lot of them. And I really want to point out that there are a few phase curves thrown in here, some of these blue points are phase curves, but most of them are like separate programs of people doing transits, people doing emission. And I really think that if we combine our efforts a little bit more, we'll be able to provide a much tighter constraint on any possible cosmic shoreline location by combining these efforts a little bit. So just to conclude, I really, transmission and emission should be used to complement each other where possible. Generally, emission is going to be better for our hotter targets, but there are cases where transmission is still preferred. We showed the first kind of test of doing this with GJ 1132b, but I hope we can do this a lot more in the future. Thanks, guys. Questions?
Okay, any questions to transmit? No, you knew I was going to go that way.
Hi, Katie. Marco Wadriga, Scientific. Thank you very much. That's super interesting to combine these two things. Since I don't do transmission spectroscopy, I have a question that might be obvious to those who do. It's not. Can you help me understand intuitively why lower pressures are easier to probe with transmission spectroscopy?
Yes. So within transmission spectroscopy, if it's a higher pressure, higher pressure is always better. It's always going to be higher signal. However, if you're comparing between transmission and emission and you have a low pressure, transmission is easier because we're inherently probing lower pressures of the atmosphere through that slant geometry of the transit, as opposed to in emission, you're actually probing a bit deeper down. So you're less sensitive to the more tenuous outer layers.
Cool, thank you.
Emily Patton at MIT. I was curious what you mentioned when you're showing your summary of the different planets that come in all the phase curve. I was wondering if you could speak a little bit more on how useful is that in shaping the structure, having that data? Like obviously
sure. Yeah, right. It would be great if we had phase curves for every single thing. Yeah. I mean, I think that I think that phase curves can certainly help provide the stronger constraints, particularly on the day side and the night side temperature constraints. So it's also a really great way to break, because there's the big degeneracy right between like the albedo and the heat recirculation. So if we had phase curves, it would be awesome to provide even tighter constraints. But in lieu of that, I think that at least starting with a set of transmission and emission is a good place to start. And I think too, if you had something like if you did have a hint of an atmosphere and you had the transit and eclipse, I mean, it's a shame that those hadn't already been put together in a phase curve, but I think that would provide a good motivation to go deeper dive. Yeah, I'm becoming a quick convert to phase curves. So.
I'll ask one. The thin atmosphere, the low atmosphere, you're saying you can, let me collect my thoughts.
Yeah.
What I'm thinking about is our worlds like Mars in our own solar system, 6, 7 millibars.
Yeah.
Not detectable here right now, but have dust devils and global encircling dust storms and a variety of clouds and a rich, interesting atmosphere.
Yes.
How can we get down to those pressures?
Yeah, I have heard some talk about, well, you said the dust storms, and I want to, my mind is going there, because there is talk of like trying to use emission to measure dust storms on planets. But yeah, how can we get down to the lowest pressures? I mean, I think honestly right now, I think the answer is that we probably can't unless we want to, do like 40 transits of a planet. But I think the point is that instead of the cosmic shoreline being like, yes, atmosphere, no atmosphere, I think a good approach is like, okay, only millibar atmospheres are possible across all composition regimes. Like if we approach the cosmic shoreline more as like providing these limits, I think that is a little bit more realistic for now.
Okay, yeah. Great, wonderful. Let's thank Katie one more time.
You guys.
Okay, next up is Kevin France. Perfect. And title of Kevin's presentation is the escape driving properties of planet hosting G, K, and M stars, what we know and what we would like to know.
All right, thank you, Dave. So I modified my title a little bit after I saw what some of the earlier talks were. If I'd have known we were playing this game, I might have made it a haiku or something. But I'm going to talk about the escape driving properties of cool stars. So this is a talk that's a combination of observation and analysis to build stellar spectral energy distributions, how they vary in time, and other properties of the star. And when we run into roadblocks, to think about what type of new experimental techniques we would need to unblock those roads, and then connect that to atmospheric modeling. So there's been a ton of great introduction already this week, so I'm just going to sort of mention this high-level plot that says what we've all been saying, that the star plays a very important role for all sorts of different aspects of exoplanetary atmospheres. If this were a different sort of exoplanet meeting, we might be talking about the near UV and far UV driving photochemistry. But since we're at an atmospheric escape meeting, we're going to talk about the higher energy particles and photons that drive the ionization and heating exoplanetary atmospheres. So I thought about different ways to present this, and at the end of the day, I decided that we were probably going to be talking about the cosmic shoreline a lot, so I went ahead and thought about presenting this in the context of the cosmic shoreline. This is a figure that I stole from one of Megan's papers. So as we know, there's a simplified framework to understand which planets may host very thin or no atmospheres whatsoever. And it's a balance between the planet's gravity, shown as the escape velocity, and the stellar energy input. So the idea, right, is if you're on this side of the shoreline, that your atmosphere survives. But if you're over on this side of the shoreline, it's unlikely that you maintain an atmosphere. So this plot has two axes, and the y-axis is usually taken as the cumulative XUV irradiation, so the integral of the XUV radiation that a planet receives over time. So the things that we need to be able to understand this y-axis from the stellar perspective are things like the present day XUV, how that XUV changed in the past and maybe what it's going to do in the future. And then I'm going to lump a few things in here, any other factors that increase or decrease the escape rate. So let's talk about these two first. So this is the XUV, right? XUV is X-ray plus EUV. These dominate the heating inputs to Earth-like atmospheres. Again, we can have sort of a different talk about Jovian planets, but I'm going to focus mainly on Earth-like atmospheres for this talk. So this is two parts of, these are not the same wavelengths as Ruth and Renata described yesterday morning. So I'm going to mention something again about the differences between the EUV and the X-rays. One, as Ruth said, that the photoabsorption cross-sections are much higher in the EUV. And partially as a result of that, the EUV photons are absorbed much higher in the planet's atmosphere. So I want to show that graphically. And so what I'm showing here is a plot of the relative photoelectron energy distribution after the ionizing photon comes in and produces a photoelectron as a function of the wavelength of the incoming photon and the altitude in an Earth-like atmosphere where that happens. So as you see here in the X-rays, right, we deposit a lot of energy low down where it's really balanced by efficient cooling. So we don't give a lot of energy there to drive atmospheric escape. And then here in the EUV, right, we deposit a lot of energy further up in the atmosphere where it can drive heating and ultimately lead to all the different escape processes that we've been talking about. One thing that I want to sort of draw your attention to here is that this doesn't happen at one wavelength, right? A lot of times, and in all of those energy limited escape formula, you see F underscore XUV or F underscore EUV, like it's one number. It's not one number. It's a spectrum. And if you don't have a spectrum, then you're probably missing some of the relevant physics. And Ruth and Renata also spoke to that yesterday morning. So the last thing, as I get myself hung up there, is from the star, there are more EUV photons on every type of star than there are X-ray photons. So it's possible, it's maybe debatable still, if maybe very young stars have higher X-ray luminosities, and right, X-rays can create multiple electrons, but there are more photons to do the work on all types of, in the EUV on all types of stars. So, okay. So then the next question then, if we're going to separate XUV and EUV, I'm going to sort of make the assertion that the EUV is probably the more important one. So question number one is, what do we know about the present day EUV spectrum of other stars? So I think this is best captured in the rather famous Sun and Time paper from 20 years ago. This shows what we know. This is just solar type stars. Here is the EUV, 100 to 360 angstroms, and those 4 stars are the 4 solar type stars. One of them is the sun that we have EUV spectra for. There are about another 4 or 5 very young active M dwarfs where we have EUV spectra of like a few ratty emission lines. So that's it. That's it. So we have 6,000 exoplanets and like 6 stars where we have the EUV inputs. So yeah, I said 5. Maybe it's 6. Maybe it's 7. Whatever. It's astronomy. So these are the stars we have from this mission called EUVE. This is the only extreme UV astrophysics mission that's flown. That's a really small number. So why do we have such a small number? Well, the interstellar medium is a high opacity source, or there's the cross sections for neutral hydrogen and helium sit there. But more important than that, we've just never really looked very carefully, and I'll come back to that in a second. So what do we do because we don't have actual observations? Well, we tend to develop scaling relations based on other emission lines and different bands. So here's one example, right? I'm giving the talk, I'm going to show my example, right? So and why does this kind of work on a broadband level? Well, it's because you can have emission lines in different parts of the stellar atmosphere that are formed at similar temperatures. So at a broadband level, this kind of works within factors of a couple uncertainty. There's lots of other approaches. There are semi-empirical models. There are differential emission measure models. And Cindy Froning's poster has some of this. And then lots of references to this in the literature. But let's move forward, though. Let's assume that we can estimate this broad EUV coverage with scaling relations. So what about the history? Right, so this is an updated EUV history of solar type stars that we published this year. Right, this is characterized, as many cool stars are, by a saturated regime early in the star's lifetime out to maybe 75 or 100 million years, and then a spin down that happens after that. So if you're interested in the cosmic shoreline, right, you need a figure like this so you can integrate backwards over time. Now this is for the sun. If we put M dwarfs on this plot, right, we see a couple of things right off. First, they spin 10 or 20, or as Emily Pass showed us from H alpha, maybe 40 or 45 times the solar lifetime in the saturated phase. The saturation level is different, and they have a different fall off afterwards. So M dwarfs are going to definitely have a lot more integrated XUV, right, normalized to the habitable zone than solar type stars. Okay. Let's come back here. So we've talked about 1 and 2 already. In my last couple minutes, I want to talk about these any other factors. And I'm just going to lump these as time variable terms. There are stellar particles, stellar photons that change in time. A super important thing that Shannon mentioned this morning were stellar winds, with sort of steady state stellar winds. You can ask me about that later, and I will mumble a dissatisfying answer. So what do we know about things like the CME properties of other stars? Well, not very much, right? This field there are lots of observational attempts to find CMEs or solar energetic particles. I'm just going to show you one example of maybe some probably pretty good circumstantial evidence that we're seeing CMEs now. So this is on a very young solar type star. So you see a quiescent, big flare. And what we're seeing here is strong blue shifts now in some of the transition region lines of a couple hundred kilometers a second. We do this from HST and from the ground, and we see a time delay, and then we see the cooler CME emission coming after that. So, or sorry, that's actually the CME absorption we see after that because it's against the photosphere. So I'd say that there's a lot of work to do here. We still aren't seeing CMEs the way that we do on the sun. Okay, what about flares? Well, we know young stars flare, right? This is AU-MIC. This is a far UV light curve. It flares all the time. Bad news, old M dwarfs flare pretty much just as frequently, but they aren't quite as energetic because they don't start with the same basal flux. But you can use that to model what the atmospheric escape rate would be from an Earth-like planet put in the habitable zone around even one of these old stars. And right, you get kind of like Earth-like escape rates in quiescence. But when you include the effect of flares, you can get pretty dramatic escape rates from both thermal and non-thermal processes. I think we heard the poster presentation yesterday that said that this doesn't happen. I think that there's a lot of devil in the details about exactly how you do this. I think Laura Amaral is going to speak to this some tomorrow. It may be that actually this time variability doesn't matter much. If you go see Dave's poster from the RAPS team, it says that it's probably unlikely that even in the quiescent case, that a rocky planet is going to be able to maintain an atmosphere around this planet, this type of star. All right, so let's bring all these things together. So here is another cosmic shoreline plot. I just picked another star because I knew somebody was going to be talking about L9859. So there's a lot of things that are uncertain about the y-axis. There's the scaling relations, right? So factors of 3, 5, 10. There's the different XUV history. So that's going to probably bump you up another factor of a couple. And then look. Oh, even on this old star, it also has X-ray flares. Oh, just those old stars. So look, it's spinning, right? That's how serious it is. So there's this other uncertainty about the flares and CME contribution, right? So all of these things are going to compound. And this is for M stars, right? The story is probably not so bad for G stars. I think K stars is maybe still TBD. So what can we do to solve these problems? and reduce those uncertainties? Well, we could build a dedicated mission. Park talked about this yesterday. This is the ESCAPE concept, where we would go out and directly measure EUV and FUV spectra for over 300 cool stars, and also do deep monitoring observations to find CMEs and quantify these flare rates. If you've seen me give one of these talks over the past 10 years, you're probably thinking, he's still talking about that? It's worse for me than it is for you. So this mission was selected as one of the 2 missions for Phase A in 2020. We ended up coming in 2nd place, and so we're trying to repropose it, but NASA keeps pushing back the deadlines. So when you can do this many, so how do we do this, right? We get factors of sort of 50 or 100 more sensitivity than EUV by an updated instrument design. But once you've been able to put statistical number of stars, hundreds of stars on a plot, you can start actually laying out the history, EUV history, as a function of spectral type. And so this would basically be the thing that would allow us to treat M dwarfs, K dwarfs, F stars, everything systematically. And the last thing I'll say about this is that this is also the most, I would argue, the most promising way to do direct CME observations using sun as a star techniques that we've actually validated in our own solar system. So the idea is that when a big CME goes off, you get this dark hole. This is called a dimming, coronal dimming. And the Solar Dynamics Observatory has now observed and characterized hundreds of these. And this can actually be done if you go into the EUV with spectroscopy. So we would imagine these really deep monitoring observations to find the CME rates on solar type stars, M stars, are they, and then understand how activity plays into that. All right, so I'm running out of time, so I think I'll just leave up my conclusions and take questions. Thanks.
All right, thanks, Kevin. We have time for 1, maybe 2 questions, and there's a whole array or spectrum of possibilities. So, here you go.
Okay, Dave, Charlotte, Harvard. So if we look at the optical, we see that the flare rate from M dwarfs follows the saturation relation. It's they all have the same flare rate, and then once they spin down, it falls dramatically. Barnard star absolutely falls off the cliff. No optical flares, very, very rare. You said the flare rate doesn't depend on age or rotation in the high energies. It just keeps going. How do I reconcile those 2 statements?
Yeah, that's a good question. I'm going to defer to Park on that one. Yeah, no, it's a good question. I mean, this was one of the biggest surprises when we first started doing these early muscles projects, is that they all flare, every single one of them. And you don't have to observe them very long. In a couple orbits, they're all flaring. So, I think that in part you don't see the same small flares on younger stars because the basal level is high, but we definitely don't see any M star population where the signal to noise is not terrible, where you don't see flares in the UV. Yeah.
Okay. But is it a different mechanism? Like I'm telling you, they do not.
I understand. Yeah. Well, I mean, I think even
a factor of 5,000 is how much they go down. And you're saying this, so it's just fascinating.
Yeah. Yeah, I mean, even within this high energy band, right? There are flares that happen only in the FUV and don't have X-ray counterparts. There are those that do the reverse, and I don't have a good answer for that. Yeah.
Okay, I'll take chair's prerogative and do 1 more. Apologies, I'm taking hands in the order that I saw them. So, Jen, yeah.
First of all, I hear your pain about potatoes. A question about. This is kind of a general question even to the room, to understand how well do we need to really know the EUV flux? Because the uncertainties that we've been seeing throughout the talk are very high. The uncertainties that we're going to be able to observe potentially are also high. So how small do we need to get them in order to answer the questions we were talking about yesterday?
Yes, that's a great question and something I thought a lot about. I think the answer is about a factor of 2. I think when you start to talk about factors of 2, those are the levels that when you get to factors of 2, 4, 5 times the present day EUV flux of the sun, you start to get dramatic changes in the escape rate. So the real question is, right, like how much do you need to change the EUV before the planet's atmosphere responds dramatically, right? And it's factors of about 5, 4 to 5. And so I think that you need to know this. So the star is not the driving uncertainty in that process. I think you need to know it to about half of that. like is Nyquist sampled, right? You want 2 points across the uncertainty.
All right, let's thank Kevin one more time. Okay, and the final presentation for this session is being given by Johanna Teske. Titled is A Thick Volatile Atmosphere on an Ultra-Hot Super Earth.
All right, thank you. Okay, so can everyone hear me? Okay, yes. All right, great. So I'm going to be showing results from a JWST Cycle 2 program, which is a near-spec G395H phase curve. I don't have the phase curve results to share yet, but I have the emission spectrum, so one step at a time. This is an artist rendition of 55 Cancri E. We have an artist rendition of the system that I'll talk about, but it didn't get into the press review before the government shutdown. So I want to pre-thank the Space Telescope press team for working with us and sticking with us, and hopefully that will be out soon. I also want to acknowledge all the staff here and folks who are running the conference, really appreciate it. And the team that I've been working with, so Emma is here this week and will give a talk on Thursday. Bo is here and has a poster. And I also just want to highlight Nicole Wallach, who is a postdoc at EPL on the job market, who did a lot of the observational work for this study. I wanted to actually have this paper be the TOI 561b near-spec team as the first author, but WS wouldn't let me do that for a 13-person team, unfortunately. That's the way it was. And then Samuel and Alex are working on the phase curve results. So like I said, stay tuned for those. We wanted to have kind of a top level result out before the cycle 5 deadline. So that was the motivation for the paper that is accepted and on the archive. So just setting the stage a little bit, switching gears, why am I going to talk about an ultra short period planet? This is an atmospheric escape conference. These ultra short period planets are obviously very hot. They have day-side surface temperatures exceeding the melting point of rocks. They're not common like sub-Neptune planets. They're somewhat rare, kind of similar rarity as hot Jupiters. A lot of signs point to them just being bare rocks. But there is a subset of these that are kind of anomalously underdense, and so have densities more consistent with not just a bare rock or a silicate-like or even Earth-like composition, but consistent with having a magma ocean that has some amount of volatiles contained in it. And so that could be important. We think magma oceans, as we'll I think hear about in the next session, can be these reservoirs of volatiles. They can hold on to them for a long time, and that could impact the interior geodynamics and geochemistry of the planet, and maybe link it then to the atmosphere to the interior. So 55 Cancri E is one example of one of these types of somewhat underdense ultra short period planets. And JWST observations suggest that it might have an atmosphere, or likely does. Another example, which I'll talk about today, is this planet TOI 561b. So this is another ultra short period planet, 0.44 day orbital period. Very, very hot. It's one of, if not the hottest, at least when we proposed, ultra short period planet. It's also quite small, you can see, very different than 55 Cancri E. Another thing that sets it apart is that it orbits this thick disk star. And so this star is very, very old, and it's quite chemically different than the sun, and also 55 Cancri E. And so this is just an interesting comparison study for the ultra short period planet sample. And so the question we wanted to answer was, what's responsible for this underdensity? Does this planet have an atmosphere that could explain its high radius given its mass? I'll just preface this by saying I have looked at other JWST results for some Neptunes and rocky planets, and I've generally been like, I've been somewhat disappointed, I'll be frank, in that we've seen lots of flat lines. And so going into this, Anjali Piet pointed this out to me and like, oh, we should go after this planet. I was like, well, is the mass right? Is the radius right? I don't know. I was like prepared to just have a result that was slightly underwhelming for this planet given my experience thus far. But let me walk you through what we've seen. I'm just going to basically step you through the emission spectrum. So this figure is going to gather more and more components. So like I said, this is just the first results, the emission spectrum. These are 2 different reductions. And obviously the first thing we notice is that this is, the emission spectrum is much lower. The planet to star flux ratio is lower than a zero albedo bare rock. So that is curious. And this is by quite a lot. The next plot's going to be a little painful, so just be prepared. This is what the white light curves look like. So we know that this does not look great. There's definitely correlated noise. It turns out, like, even for a quite hot planet, this is very challenging to do, even with JWST. We have 4 eclipses in the phase curve. So it's rough. We recognize that. Because this is such a short orbital period planet, we also tried fitting these secondary eclipses with more of a model that you might see for a full phase curve observation. That's not what I'm showing here, not the full phase curve, but including some of this baseline curvature that makes more sense potentially for such a hot short orbital period. And those are the triangles in this plot. And so that does change the emission spectrum slightly, especially in NRS1, where we think the systematic noise could be higher, and maybe even like stellar surface inhomogeneity would be more of a factor at slightly bluer wavelengths. But anyway, still below bare rock. Okay, definitely correlated noise. So this is, I guess, what's formerly known as an Allen deviation plot, but normalized RMS versus bin size. The bold curves are the white light curves. This is for each eclipse, and then the spectroscopic ones are in slightly less bold lines. And so, yeah, definitely still correlated noise. The straight black line is what you'd expect from just white noise. And so we tried a prescription that is described in the paper. It's not super complicated, but basically trying to inflate the errors to account for this difference between the noise that we see and what we'd expect from white noise. And those are these red points here. And so the error bars are definitely larger, but still well below a bare rock. And so, the eclipse, or the fit with the baseline already included errors that are inflated with this factor. So our analysis basically consistently finds that it's inconsistent with the bare rock. If the eclipses were smaller, if they weren't detected, that would just push things farther down. And in this case, because we have a phase curve, we don't have this issue of like maybe missing the secondary eclipse because of uncertainties in the timing or the eccentricity. So we're sure that we're measuring, we're sure that we have the eclipse. And so you might ask, well, this is a bare rock with this assumption about the bond albedo. So what about a black body surface with a high bond albedo? Could that just shift this curve down and match the spectrum? This planet is so hot that the surface would be vaporizing if it's rock. And at these temperatures, that rock vapor atmosphere would be optically thick due to like SIO and MGO opacities between 3 to 5 microns. And so that spectrum is still going to be set by the rock vapor atmosphere rather than a reflective surface. I think also there have been some studies that have suggested like a magma ocean surface would have rather low albedo also. And anyway, we tested a thin rock vapor atmosphere model, or we compared it to the data, and that also seems to not match here. Maybe some of the NRS2 points are matching or overlapping, but it's not super consistent. And also, I forgot to point out before, this is the difference between NRS1 for near spec and NRS2. So this is not a detector jump. All these 4 points are on the same detector. So what about a thin rock vapor with reflective clouds? It's unclear whether those types of condensates could stay aloft. Also, due to the very hot temperature of the rock vapor, they might only really be able to condense on the night side of this planet. Again, very short orbital period, obviously tidally locked. And there's been at least one paper suggesting that heat advection could offset that cooling in a partial rock vapor atmosphere. All that being said, it's still at odds with the low density of the planet. And so this is something we might explore a little bit more in a follow-up paper, a rock vapor atmosphere with clouds. But we think that the explanation that's most consistent with all the evidence that we have so far is this volatile-rich atmosphere. And so in this figure, we're showing just like a smattering of different possibilities. There, like I said, is going to be follow-up work that goes into this in more detail, exploring much more of a parameter space. But we're suggesting that kind of this family of models is what's most consistent with the emission spectrum. Now, we're also suggesting that the source of this would be those volatiles that I mentioned that would have been locked up in the magma ocean. This would have to be over gigayears. Remember, this is a thick disk star, so the star is like 10 gigayears old. So this is still very puzzling. How did this planet hold on to its atmosphere? That's why I'm giving this talk at this meeting. I need your help answering this question. We haven't explored planetary magnetic field. Could there be a late delivery of volatiles to this planet? There's also several papers that suggest ultra short period planets don't form, obviously, at their very short periods, but may have spent a large part of their lifetimes at a few day orbital periods and then migrated inward quite late. And so maybe that would help this planet retain an atmosphere for so long. I'll just point out very quickly that maybe I shouldn't have been so surprised by this result, because it appears that some of these other very hot planets have observed brightness temperatures that are below their irradiation temperature. And so maybe we're starting to see that these very hot planets are able to replenish atmospheres faster than their loss. We've seen this cosmic shoreline plot several times, and so I'm interested in what these types of planets might mean for the cosmic shoreline. It's a very different regime, but it might mean that we could find planets around, or atmospheres around more planets than we would originally expect. So this is the takeaway. The paper is on the archive. This is the question I need your help answering. Emma will also be leading a kind of planet evolution paper, but I think there's a lot to explore here. And I hope that this planet can be a case study for coupling atmospheric escape with geochemical evolution in an environment that's quite distinct from the sun, which I think we'll hear more about this general topic in the next session. So thank you.
Great, thank you. We have a short period for questions.
Good.
Yes. Thank you. Lonely, John Hopkins. My question is very simple. So if you take into account the curvature of the phase curve, how does it change the emission spectrum?
Say it again.
You take into account the curvature of the phase curve, because you expect just relative measurement in and out, right? So the curvature will raise the baseline, so presumably.
Right. So that's sort of what we tried to do with that. It would be the points, the triangle points here. The fitting of the entire phase curve is still, that's not ready for public consumption yet, but it's not inconsistent with what we're finding by what I showed, like just fitting the eclipses, but including a little bit of out of eclipse baseline curvature. Does that answer your question? Okay.
Great.
Yeah, nice talk. So quick question for the temperature, the 2300 Kelvin is what you predicted just basically before this observation, or is that derived from?
No, that was just predicted before the observation.
So what's the new brightness temperature?
Oh, good question. It is in the paper. It depends on obviously which reduction you use, but we have the distributions at the end of the paper.
Okay, thanks.
Hi, yeah. So what is this rock vapor? Because sort of vaporized things like SAO do have spectral features, I think mostly in the LRS bandpass. Is that something you're thinking of following up? Right. Or is there some, like, sort of low?
Yeah. There are some SIO features. I don't remember exactly what combination Anjali used model, but they're more prominent in the LRS bandpass. Does that answer your question? Okay.
Great, and I'm happy to talk about this one off.
Okay, cool.
So with that, let's thank Johanna again. And because we like clapping a lot, let's thank all the speakers in the session one more time. And then one or two quick things before we send you off to lunch. One is I did my best to make sure I'm never invited back again as a session chair. Hopefully that worked. Number two, I'd like to remind people or tell people that there are as many as 3 faculty positions that are open at the University of Colorado or soon to be open that would be of interest to this community. So feel free to come find me at a break to ask about those. 2 of those are on the same ad. They're at LASP at the University of Colorado, which is a research institute, and those ads are for atmospheric science. But the new director of LASP was very adamant that that ad included wording that opened it wide enough that people who study planetary and exoplanetary atmospheres are encouraged to apply. That closes very soon, like 4 days or something like that. And there's an ad coming from the Department of Astrophysical and Planetary Sciences that is for any topic that our department covers. And I think it's okay to say that the faculty in the department have definitely discussed exoplanets as a topic of need for the department. So feel free to ask me about those or what the difference is between a research institute and a department at CU. It's very confusing. And with that, any other, great.
Third announcement, I've been getting lots of questions about bingo. There are prizes, but in order to qualify for a prize, you literally had to shout bingo if you get it. But, well, you had to shout.
No, I don't have.
Oh, you don't have a bingo yet? So raise your hand whenever, if you get bingo. Maybe you don't need to interrupt the talk for that, but at the end or during lunch, you can shout during lunch but yeah, raise your hand. But there are prizes, so.